Welcome back to BE 110. Today we're going to derive the conservation of momentum laws for continua, starting with the conservation of linear momentum. Previously, we derived the special case of conservation of linear momentum for a body in static equilibrium. Today, allowing for accelerations and therefore inertial forces, we'll derive the full equations for conservation of linear momentum. And in words, this statement will generalize to the following. The rate of change of linear momentum of the particles that instantaneously lie within a fixed region R is proportional to the resultant of the body forces acting on R together with the resultant of the surface tractions acting on the surface S. So mathematically, we can write this as the material time derivative of the triple integral over R of the density rho times velocity v with respect to volume is equal to the triple integral over R of the density times the body force with respect to volume plus the double integral over S, the surface, of the traction vector T integrated over the surface. So the first term are the inertial forces, the rate of change of mass times velocity. The second term are the body forces, the integral of the body forces per unit mass times mass per unit volume over volume. The third term are the surface traction, or the surface forces, the integral of all the surface tractions over S. Expressing this same equation in index notation and using Cauchy's law to convert traction into stress, making use of the unit normal n to the surface, where t, little t, is equal to n dot big T. We'll obtain material derivative of the triple integral over R of rho vi with respect to volume is equal to the triple integral over the region R of rho vi with respect to volume minus the surface integral of tji nj, which is the surface tractions in Cauchy's formula. Now, as we did before when we derived the equilibrium equations, we apply the divergence theorem to convert the surface integral into a volume integral, which will yield three volume integrals that we can collect together as a triple integral over R of rho dvi dt, that's the inertial force term, minus rho b sub I minus del tji del xj, where this is divergence of the stress tensor integrated with respect to the volume is equal to 0. Now, as we've done before, we note that since the region R over which this integral must hold is entirely arbitrary and so it must hold for any and all regions, that means that the integrand itself, expression inside the integral, must be 0. And hence we obtain the familiar differential form of the conservation of linear momentum, that del tji del xj plus rho bi, these are the two terms that we already derived in the equilibrium equation, are equal to rho times material derivative with respect to time of the velocity, which is the acceleration, so rho times acceleration, where ai are components of the acceleration vector. So surface forces plus body forces equals inertial forces.